أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم Assalamu alaikum. Welcome back again. In the last video we have learned about how to design the power dividers, Wilkinson power dividers and so on, and other dividers also. There I think I have done one small mistake, that I didn't use this uh, equation to find out the value of R. So here I have corrected this one here. So 50 ohm K plus 1 by K, which gives us this value, and then if you multiply with this one we get this ohm. Now remember one thing, that after this solution you have to draw this figure and you put these values here exactly. That is called illustration of your solution. It will be asked in the exam. So after you finish everything, you need to draw this one, and then you put these values, corresponding values here, will complete the solution. Otherwise you will have partial points. So it was the video was until Wilkinson power divider. So today we will move on to the directional couplers. Okay, here we will do one example for directional coupler. So this is the first type of directional coupler, which is called branch line quadrature coupler. We call it also 90-degree hybrid directional coupler also. This is a solution. This is an example from 7.5 David Poser book, chapter 7, number 5 example. So I will not go for very very long and tedious derivation. So this should be the structure of the branch line coupler, and in this branch line coupler you can see that there are 4 ports. Input port, which is matched with 50 ohm, output port, which is matched with 50 ohm, another output port matched with 50 ohm, or these all are actually Z, means like it can be 50 ohm, or it can be other if it's mentioned other ohms, like since we told that this is 50 ohm, so this Z0 value is 50 ohm, and all these 4 actually 1 2 3 4 are actually matched with 50 ohm. This line is 50 ohm also, but we need to calculate the length of this line and the impedance of this line. Okay, so this is after long and all derivation and analysis of the odd mode and even mode and all the other things, we get at the end that a directional branch line coupler, which is quadrature hybrid, can be designed like this. So you have to remember this one, since the exam will be open book, so no problem. So 2 more things to design this one. We need to find out only 2 more things, which is what is the length of this line, both line, and what is the impedance of this one, or what is the width of this one, if asked, because you know from the chapter 3 or 2 I think, how to design the width of this one if the characteristics impedance is known. So let's go to the solution. That what we have here, we have a Z0 of 50 ohm and a frequency of 3 gigahertz. So the lambda is 0.1 meter, means 10 centimeter, I think. Yeah, it is 10 centimeter. So the length of this one, L, is lambda by 4 divided by 4 is 2.5 centimeter. So the frequency if different, then this will become different. Now it's time for us to find out what is the impedance of this line, means the characteristics impedance of this line is following Z0 by square root of 2. So Z0 we know 50 and we divide it by square root of 2. It gives us 35.36 ohm. So that will be the part of the directional coupler branch line design, But however, remember one thing, in the test maybe it will be asked that what is the width, find the width of this line. So this is the extension of what you know already, so I didn't include in the solution because I have already teach you what is the how to calculate the width um, of this line if you know the impedance with the frequency. So maybe it will be asked. So I will later on discuss about this in the group also. So this is as simple as that a branch line quadrature hybrid coupler can be designed like this, where the length needed to be found and these two impedances of these two characteristic impedance of these two different lines are this one. So this is the branch line coupler is done. And then we move on with the coupled line coupler, where the coupled line coupler somehow look like this, which have a 4 different port. Port 1 is the input port, and this is the coupled port, means if we give an input, let's say it is 20 dB coupler, it means the coupled, if we put 0 dB here, then minus 20 dB, 0 dBm here, then minus 20 dBm will be coupled here, and the rest will be with the through port, and nothing will theoretically go here. Similarly, if we try to give some input here, some part will go there, but nothing will, it will come out here, but nothing will come here. So basically, but usually we don't use that one. We use for one directional only because it's a directional coupler. We use circulator sometimes for that type of things. So in this structure, there are 4 ports for sure, and then for 4 port, there will be coupling will be given. From the coupling, we need to design this one. However, we need to find out what is the separation between these two lines, what is the width of this line, and what is the length of this line. So let's go to a problem and then example actually, and we go there and try to find out how to solve this one. This is an example from David Posner book. You can find this example in the Posner book, where we need to design a 20 dB single section couple line coupler in a strip line with a ground plane spacing of this. It means this is D. Sorry, this is B. Ground plane spacing means B. A long time ago, actually, I teach you how to design this one. However, the dielectric you need to go back actually to learn about it, but no need here, no need to be concerned so much about it. So the ground plane spacing is given B, okay, and the dielectric constant is given. A characteristic impedance of 50 ohm is given, and the center frequency of 3 gigahertz. So no need this part. We will solve only this part. So what we need to find is we need to find the L, the length of this design, length of this section, both of they are same. What is the separation between these two lines, coupled lines? These are two coupled lines. And all the widths, what are the widths? Because all the widths are the same. So if we find one width, means all the widths are the same. So now we extract what we have here. So the coupling is given 20 dB. So C dB is actually coupling in dB here. The frequency is given 3 gigahertz. Line impedance is given 50 ohm. Spacing is given 0.32 centimeter, and then the dielectric constant is given. So we will find out what is the S, what is the W, what is the L. Let's go to the solution. I didn't actually derive these two equations because it's very tedious to do it, but you will find these equations I think in the book. Okay, even and odd mode equations. So this is even mode equation and this is odd mode equation. We need these two values actually, but I will come back here later on. First, what we have to do from the coupling. From the coupling given, we need to convert it to voltage coupling, because this is coupling in dB, right? So we need to find out the coupling factor in voltage. So we call it voltage coupling factor. So we need to find out the voltage coupling factor, where C is equal to actually 10 to the power minus 20. 20 means the giving C, you know, this one. If it's 5, then it should be 5 here. Okay. If it's 10, then it should be 10 here. Okay. So since it's 20 here, so we put 20 here, divided by 20 means minus 1. 20 to the power minus 1 means the C is equal to 0.1. So this is our voltage coupling factor. Now with this voltage coupling factor from 7.87, you'll find it these two equations in the in the book, David Porgier book, chapter 7. The even and odd mode characteristic impedance we need to find out. So for even mode we put C here, the values here, and then we get 55.28 ohm. And then we find the even odd mode impedance, which is 45.23 ohm. Now this one is figure 7.28 from David Porgier. We need to use these values here, but before that, because let us understand this figure first. This figure is square root of the dielectric constant multiplied by even mode impedance, and the same thing with odd mode impedance. So dielectric constant, square root of dielectric constant multiplied by Z even, and square root of dielectric constant multiplied by Z odd and Z even. So this is this versus this one. So to determine something, we need to find these two first. Since we know what is our Z even and Z odd, so we just multiply. Since we know that our dielectric constant is 2.2, so here we put the value 2.2 and here 2.2, and we multiply with this. This we get 82 and 67.1. So let us find this one first, which is 82 here. So we draw a line here, and this is 67.1. So 67.1, somewhere here is it not needed to be so exact, you know. It's not necessarily have to be so exact. So now we draw two lines and then they intersect in one point, right? So in that one point we need to find out our See here, it is W by B. This line is W by B line, width by the spacing. Spacing means this two conductor spacing B. And this one with this one is actually following the value of S divided by B. S means the spacing between these two conductor. So this one is W and this one is S here. So now we need to find two different values from these two different this versus this plot. So now we are here. This is our intersection point, right? So in that intersection point, we are a little bit slightly over than 0.8 at this line. Means the W by B should be 0.8, like let's say 1 or something, 805 or something. Here they have chosen 0.809. If you choose 0.8 is okay also. So we have this value, and then from this one we go like this. You follow this curve, not straight, you try to follow like this, and we find here 2 point, more than that actually, 3, around 3, say, because if you're here, maybe here 3 and then it's 4 and then it's 5, right? So around 3, so 3 point something, or just put 3 here. They have chosen 0.36. If you choose 3.1, no problem. If you choose 3, no problem also. So here we already got these two values, and since we know about B, our B is given as 0.32 centimeter. So we multiply this value with B, we get W of 0.259 centimeter. And the B value we multiply with this value, so we get the spacing, means the separation between two conductors, two coupled lines, is this value. So now we have this. So our W is 0.259, S is 0.098 centimeter, all are in centimeter, and the L is 0.25 centimeter. So let us draw the circuit. The circuit is like this. So we have 2.5 centimeter long, this one, and the width is 0.259 centimeter, and the spacing is 0.098 centimeter. So this concludes the lectures actually. All the lectures is done. I will put up one more video about the tutorial and the suggested practice there for this. So you practice well, and if you have any question, you can ask me. In the tutorial, I will try to solve 2 more problems with the 4-port divider and couplers, and one with the multi-section couplers. So see you in the next video. Assalamu alaikum wa rahmatullah.